We can start.
I'm good. Okay, well, thank you very much, Salvatore. It's a real pleasure to be able to talk to you today. Of course, I would prefer to be there in person, but it would take several days, and thousands of dollars. And here we can do it for free in a very short period of time. So, and what I want to do today is talk to you about the evolution of plate tectonics over the past 2.5 billion years. And this is sort of a different approach than you'll see often in the literature, where people argue about when plate tectonics started, and most people put it in the Archean. And okay, that's fine, but I approach this problem differently, basically working backwards from today. So let me explain, get going. So let's start off with Earth history. So we know well the fourfold division of Earth history, that Earth started 4.56 billion years ago, and then went through a very interesting period in the Hadean, and then the preservation of rocks, not just zircons, but rocks, beginning about 4 billion years, and then uh, significant transition at 2.5 billion years into the Proterozoic, and then into the Phanerozoic just about a half a billion years ago. So we're going to be discussing Earth's tectonic history, which is, of course, a topic of widespread interest and great controversy. So we're going to be talking about this youngest 55% of Earth history. And, many other people will talk about Archean tectonics or even Hadean tectonics, but not me. So tectonics is not just plate tectonics, and we see these words used interchangeably. Now, this paper's actually been published. I should have updated that a few years ago. This was a definition of tectonics in the broad sense to describe the volcanic, plutonic, and thermal accretion and deformation of the lithosphere of silicate planets and moons, where the lithosphere, which includes the crust, is the more rigid outer layer on top of the more ductile mantle, sometimes called a asthenosphere. So the term tectonics is often defined to only involve the crust, but tectonic deformation involves the entire lithosphere. And the point I want to stress with this definition is that plate tectonics is one kind of tectonics, but it's not the only kind. So certainly we have plate tectonics today. This is incontrovertible. Um, and what we can see here is the Earth and its many plates, and we can define plate tectonics as not only the lateral motions involving, you know, mid-ocean ridges and subduction zones and transform faults, but also the development of a global plate mosaic. So it's not just one subduction zone or one spreading ridge that defines plate tectonics. It's the fact that it's a global network. So we've got plate tectonics today, but has it always been so? And almost certainly not. I'm hoping to convince you. So what is plate tectonics? Um, excuse me, there's something popped up here for no reason. Leave site, I think is what I want to do. Cancel. No, I don't want to stop sharing. Sorry about that. What is plate tectonics? So um, Taras Gurya and I, a few years back, defined plate tectonics to emphasize both its major driving force, which is oceanic subduction, and the global plate mosaic. And I'll just read this to you. A global tectonic system powered by subduction, in which the lithosphere is divided into a global mosaic of strong plates which move on and sink into weaker ductile asthenosphere. Three types of localized plate boundaries form the interconnected global network. New oceanic lithosphere is created by seafloor spreading at mid-ocean ridges. Old oceanic lithosphere sinks in subduction zones, and two plates slide by each other along transform faults. It is the negative buoyancy of old dense oceanic lithosphere sinking in subduction zone that mostly powers plate motions. So, which leads to the question, what other kinds of tectonic regimes could Earth have experienced? And can we recognize them in the geologic record? So, the biggest controversy in Earth's tectonic history is, when did plate tectonics start? Now, this is a summary from Richard Palin's paper a few years back, and you see that he's represented
Ah, ho
geologic time.
capito.
Excuse me, somebody needs to mute their microphone. What we can see is that it's represented as a sort of a circle. And what we can see is that um, basically everybody, it's all over the place when people think plate tectonics start, but you can see that it's mostly in the Archean, 90% of these. And so, just full disclosure, there's a couple of lunatics, and actually there's only one now, that thinks that plate tectonics, the modern episode, began much more recently. Warren Hamilton was also in that group, but he passed away a few years after a remarkable career. So I'm well aware that my opinions are controversial, but that doesn't mean they're wrong, right? So maybe we've been asking the wrong question. Maybe we shouldn't ask, when did plate tectonics start? Maybe a better question is, how many episodes of plate tectonics has Earth experienced? This is a different question. So let's dig into this a little bit. If an active silicate planet, one that has convection and surface deformation, doesn't have plate tectonics, what is its tectonic style? And the answer to that is some kind of single lid tectonics. And the next question is, what is single lid tectonics? This is my definition. Other people have different definitions and use different words. Single lid tectonics contrasts with plate tectonics in that there's no global mosaic of moving rigid tectonic plates divided by weak tectonic boundaries. There is no long-lived subduction that drives horizontal plate motions. So there's lots of terms for what I call single lid tectonics, including volcanic heat pipe, which is one variant, squishy lid, which is another variant, and stagnant lid, which is the original term. But I prefer to use the term stagnant lid for dead bodies like Mercury and our moon. When I think of stagnant, I think of like a pond of water where um, you know there's no circulation and it's just smelly, or a stagnant economy, where there's not many jobs. Stagnant implies to me a kind of a stasis where things aren't changing. But single lid doesn't involve that. So just be aware that you may use different words for the same things. So it's increasingly appreciated that Earth's tectonic style has evolved over time. This is a very recent um, uh, figure from, gosh darn it, I'm sorry about my problems with WebEx. But all right, so what we're looking at here on the vertical axis is internal heating rate in watts per kilogram, so not much internal heating at the bottom, lots of internal heating at the top. And the surface yield stress, how strong is the surface, and from 0 to 300 megapascals. So what you can see here is mobile lid, which is basically plate tectonics, occupies part of this diagram, and episodic lid, stagnant lid, episodic squishy lid, plutonic squishy lid, sluggish lid. These things are all fields that have been identified. And the point isn't to dig into what these all mean. The point is that it's widely recognized that there could be different kinds of tectonic styles on any actively convecting silicate body. So this is how I see it. This is sort of the evolution of the lithosphere. So I think that the key to understanding Earth's tectonic evolution is to understand how its lithosphere evolved. So this is a complicated diagram, colorful but complicated. So what we're seeing here is time, right? Early hot to, sorry about that. Early hot to late cold, this is where we are here, plate tectonics. Back in the Hadean, we had a magma ocean, and then the mantle evolved from it, with a core, and then slowly a crust developed, underlain by a zone of partial melting with the heat pipe tectonic style, which we'll spend a little bit of time talking about, but not much. And then you see here, this is all basaltic crust and no mantle lithosphere. And then the mantle lithosphere begins to form as the body cools and thickens, right? And somewhere between, this single lit episode of drips and plumes and this one, which is with thick lithosphere with delaminations and upwellings, you have the opportunity to get the wonderful situation where plate tectonics can happen. And then ultimately, the entire mantle will cool to the point that convection is either so slow or not at all that basically there's no evidence of it on the surface tectonics. So here we've got, sort of how I see Earth evolution, and you'll notice there Mesoproterozoic Earth is sort of one of these single lid styles. So that's tipping my hand. You now know what you're going to be told. So it's basically lithosphere is going from none to very, very, very thick over time as the planet cools. So if you accept this idea that the lithosphere is going to thicken with the cooling of a body, then how can you say that the tectonic style would not change? That seems ridiculous. Seems like special pleading. All right. So before plate tectonics started, Earth had some kind of a single lid tectonic regime. And so here we're seeing, here's plate tectonic, seafloor spreading, subduction, all kinds of igneous activity. Here's a single lid representation of crust and lithosphere. There's still plenty of igneous activity and deformation. It's just different. So instead of these big sheets of lithosphere sinking into the mantle, we've got drips and delaminations that are controlling the deformation. And we have a very good example of this. The planet of Venus, this is a radar topography false color image. It shows us very well the deformation, and more important, and just as importantly, the lack of impact craters. Venus is a very active body, but it's a very different body than Earth because it doesn't have plate tectonics, and for other reasons too. So let's talk about tectonically active versus dead silicate bodies. So active bodies have surfaces preserving evidence of recent volcanism and faulting, which is evidence of ongoing mantle convection underneath. Dead bodies have surfaces dominated by impacts. There's no evidence of ongoing volcanism, faulting, or mantle convection. And we have two good examples of dead bodies, our moon and Mercury. And we've got 4 examples of active silicate bodies, certainly including Earth, but Venus, Mars, and Io, which is Jupiter's innermost moon. So Io is a good example of heat pipe. And what happens with a heat pipe is you've got all of these volcanoes and they erupt lava, and that lava flows over other lava flows, eventually depressing the crust into a zone where it's hot enough to melt and be recycled like this. There's no mantle lithosphere in the way that we think about it as peridotite. Venus is thought to be many drips and plumes and drips, that is causing these things. And the most famous of these are called the corona, which are really very interesting features on the surface of Venus. Mars has got a few good plumes and rifts. So, Valles Marineris is a wonderful, continental rift, and then you've got these big volcanoes, but there's really very little deformation. There is some, but it's very small compared to Earth and Venus. So there's 3 papers that will tell the story of what I'm going to explain to you today, which I encourage you to read if you're interested. So the first one is 2018, The Evolution of Plate Tectonics. That's where I lay out the arguments most recently for the beginning of the modern episode of plate tectonics in the Neoproterozoic time. Now that brings up a question. Okay, if it started in Neoproterozoic, what happened before? And the 2020 GSA Today paper lays out that argument. It's called the Mesoproterozoic Single Lid Tectonic Episode, Prelude to Modern Plate Tectonics. And then it brings up the question, number of questions, where people were not able to agree with me because they saw evidence for plate tectonics earlier than the Mesoproterozoic, in particular in the Paleoproterozoic. So this 2023 paper talks about this Orosarian plate tectonic episode, an earlier episode of plate tectonics, and basically that came before the Mesoproterozoic. So let's briefly review these to reconstruct the last half of Earth's tectonic history. So this first paper, The Evolution of Plate Tectonics, argues that the present episode of plate tectonics began in Neoproterozoic time. That's, I don't know why I put that in there. This is not the boring billion. The boring billion is before, so I apologize. Let's talk about that a little bit. This one is just before that. This is an episode of single lid tectonics in the Mesoproterozoic. And this one paper talks about an earlier episode of plate tectonics in the Paleoproterozoic. So that's, this summarizes it. And here we got Paleoproterozoic, Mesoproterozoic, Neoproterozoic, Phanerozoic. And no question, we have plate tectonics today. I'm going to try and convince you that the Mesoproterozoic and the boring billion was an episode of single lid, and that there was another episode of plate tectonics in the Orosarian, and that there's also evidence for a single lid episode at the beginning of the Paleoproterozoic. So and then there are these broad transitions. These tectonic transitions, for the most part, are not like a switch. You know, there's long episodes of transition from between them that we don't understand either. So, what's the basis of this conclusion? And the answer is PTIs and SLIs. And the next question is, okay, acronyms. We hate acronyms, but what are they? PTIs are plate tectonic indicators. These are rocks and minerals made by plate tectonic processes. Examples of those include ophiolites, blue schists, ultra high pressure metamorphic rocks. Those are very important plate tectonic indicators. Trace elements and isotopes are not plate tectonic indicators. They may indicate surface recycling, but if there is another way of recycling the surface, then they are not indicators of tectonics. This is a controversial point, and we can come back to it. SLIs are single lid indicators. We are just beginning to explore what these are. And we understand PTIs much better than SLIs, so let's discuss them first. So there's three primary plate tectonic indicators: ophiolites, blue schists, and ultra-high pressure metamorphic rocks. Ophiolites are fragments of oceanic lithosphere formed by seafloor spreading at mid-ocean ridges, back arc basins, and it's especially becoming clear that most ophiolites that are preserved are formed in proto-forearcs during subduction initiation. So they are clear evidence of subduction, which is expected to be associated with plate tectonics. Blue schists formed by high pressure, low temperature metamorphism of oceanic crust subducted to about 40 kilometers and then returned to the surface. So this is very diagnostic of subduction and potentially plate tectonics. And then the ultra high pressure metamorphic rocks are formed by high pressure, low temperature metamorphism of continental crust or sediments subducted to more than 100 kilometers and returned to the surface. Very famous ones in the Alps. So just to remind you what an ophiolite is, an ophiolite is, residual mantle peridotite plus gabbro, maybe some plagiogranite, some sheeted diabase dikes, basaltic pillow lavas, and some pelagic sediments, on the order of 5 kilometers thick. So very. So now if we look at the distribution of these things through time, we're going back from today back to 3 billion years ago. We're looking at the seafloor spreading and subduction indicator. These are ophiolites. And we see that there's lots of ophiolites in the Phanerozoic. There's quite a few in the Neoproterozoic. They're really quite absent in the Mesoproterozoic, not completely, but largely. And then they reappear in the Paleoproterozoic. Blue schists, the oldest one is known as about 700 or 800 million years, becoming increasingly common as we go towards today. Lawsonite bearing metamorphic rocks are very similar to blue schists, slightly different. And jadeite, which is a stone, it's a stone that's valued for its material properties by artists and others. These are only in the last few 100 million years. So these are the subduction indicators. Then the continental collision indicators are the ultra-high pressure metamorphic rocks, and also ruby and sapphire. So these are gemstones that a different community is interested in than the academic geoscientists. But you can see the ultra-high pressure metamorphic rocks appear about the same time as the blue schists, in the Neoproterozoic. And rubies and sapphires, these are things that are very common in the last 600 million years, although there's a few random ones back earlier. So if modern plate tectonics started about 1 billion years ago, okay, we don't know exactly. Let's say 800, 700, you take your choice. Does that explain anything? And I think it does. And what they are is, number one, it explains the faster rate of mantle cooling in younger times. It helps explain mantle heterogeneity, what's known as the Dupal anomaly. It helps explain the fact that while diamonds are old, kimberlites are young. It helps explain the snowball Earth, Neoproterozoic snowball Earth climate crisis. And it helps explain the acceleration of biological evolution. Let's consider each of these. So evidence for faster cooling after 1 billion years is the temperature over pressure ratio for metamorphic rocks compiled by Brown and colleagues. So this is T over P, which is degrees centigrade per GPa. It's a proxy for heat flow. And what you can see is that if we look at the distribution and do the least, a best fit to it, that it's relatively moderate here. In the Archean, it actually is increased during the Mesoproterozoic, and then begins to decrease rapidly over the last billion years or so. As you might expect, if plate tectonics takes off, because this is a very effective way to cool the mantle. So that's from metamorphic rocks. We can also look at the evidence from the mantle potential temperatures from basalts reconstructed back. Chen et al. Reconstructed it back to about 1 billion years ago. Gan and Feng back to about 3.5 billion years ago. So what you see here is the cooling rate, right? The mantle potential temperatures back 3 billion years ago was on the order of, somewhere between 1600 and 1500. And today it's on the order of, 1300 to 1400 or so. And you can see that for the most part, it looks like, this is a hint things are starting to cool off fast. And if we focus in on this area by Chen et al., we see that there was the basalts there show higher mantle potential temperatures, and then about 800 million years ago, it begins to drop off. So that suggests that the cooling rate of Earth's mantle increased in the last billion years. Now, another argument for it is the Neoproterozoic start to plate tectonics and deep subduction of continental materials helps explain why the EM1 mantle sources, from isotopic studies, the Dupal domain, are found around where the Neoproterozoic supercontinent was at about 500 million years ago. So this is the reconstruction of Gondwana at 500. Gondwana was created in the late Neoproterozoic as a result of collisions between various cratons, and that's where we see the distribution of these isotopic anomalies. So this is the reconstruction of Jackson and demonstrates that these domains are remarkably associated with where the supercontinent Gondwana, or as I like to call it, Greater Gondwana, formed in late Neoproterozoic time. You don't see them in the northern hemisphere, as might be expected. There were earlier episodes of true continental collision and deep subduction, which suggests that it didn't happen prior to the late Neoproterozoic. Now, kimberlites are very interesting because they bring up diamonds, and everybody likes diamonds. And we're quite well aware that most diamonds are very old, but the kimberlites, the things that bring them to the surface, are not. And these explosions, these are driven by incredible fluid pressures at the base of the lithosphere. So if we look at the distribution of kimberlites, they are overwhelmingly Neoproterozoic and younger. So here we're looking at two different examples. This is by geologic time period. This is by millions of years. And we see that, there are some back in the Archean and Paleoproterozoic and Mesoproterozoic, but that the huge increase in the abundance of kimberlites beginning in the Neoproterozoic. So what does that tell us about the start of deep subduction and plate tectonics? Well, if we think about it, here is the phase boundary between graphite and diamond, 100 kilometers down or so. So the pre-plate tectonic mantle was relatively dry and carbonate rich, so it was very difficult to make water and CO2 rich kimberlitic magmas to erupt through. But once plate tectonics began, you had all of this deep subduction bringing water deeper into the mantle, and that water would have eventually found its way to the base of the lithosphere, where it would build up and ultimately cause these eruptions of kimberlites. Plate tectonics, it makes it much easier to generate kimberlites. So not finally, but also a very powerful argument or consideration is the Neoproterozoic snowball Earth. And there are two main episodes in that we have to consider. One is the Sturtian, 717 to 660 million years, and the other is the Maranoan, which 655 to 632. And here you can see, the Earth covered in ice is artist's rendition, and here you can see these big glacial drop stones, very strong evidence of glacial activity, and on top of them are carbonate rocks, demonstrating, how much the climate was fluctuating during this time. So this climate crisis corresponds very nicely, with the beginning of plate tectonics in this reconstruction. So, okay, correlation is not causation. That it means just because two things happened around the same time doesn't mean one was caused by the other. However, what could have caused the climate crisis, if it's true, what sorts of things should we look for? Now, this is a table that compiles all of the possible causes of Neoproterozoic snowball Earth as we understood it back in 2018, and you can see there are extraterrestrial interpretations, there are geodynamic interpretations, there's oceanographic interpretations, there's biotic interpretations. So there's 26 or so different interpretations for what caused it, right? This is an area of active research and controversy. Now, obviously, the extraterrestrial explanations cannot be explained by um, the transition to plate tectonics, but the geodynamic ones can. You know, high obliquity, all of these things are possible results of a transition from one tectonic mode to another. The oceanographic ones as well can be related, and also the biotic ones we'll get into a little bit more. Now, this is a topic for a talk in its own right, and in fact, many causes could have been responsible for neoproterozoic snowball Earth, not just any one. All right, and then the final argument is the acceleration of biological evolution, which is widely accepted to have happened in the Neoproterozoic. And for us to accept that, or even consider that the transition to plate tectonics caused the biological explosion, we have to think about how the different tectonic styles influence life differently. So the single lid is not going to have much relief because of the elevated heat flow. You won't have the strong lithosphere needed to get great relief. The processes that lead to oxygenation, such as weathering of high relief regions, as well as basin formation and burial of organic carbon, are not going to be as strong. There's not going to be very good ways to fix CO2 compared to plate tectonics. There isn't new ways of making habitats. Moving continents around makes new habitats all the time. And the environmental pressure will be bimodal, which is it'll either be weak or it'll be catastrophic. So the catastrophic environmental pressures will be from things like large igneous provinces at this time. In contrast, plate tectonics is remarkably effective in increasing the bioactive element supply, for example, phosphorus and iron, to the world ocean. It has good ways of stimulating oxygenation through weathering and burial of organic carbon in rift basins. It has a strong climate control. It has strong habitat formation, and the environmental pressure is mostly moderate, not catastrophic. So this is really very interesting area that we're exploring in the field of biogeodynamics, and but in general, the idea that single lid and plate tectonics regimes influence biology differently is gaining increasing acceptance. So, if the modern style episode of plate tectonics began in Neoproterozoic, what was Earth's tectonic style before this? It must have been some kind of single lid. And so Mesoproterozoic single lid tectonics. What's the evidence for this? And this is where we go to our single lid indicators. So it's time to visit the boring billion. So this is just to, the Mesoproterozoic is defined between 1 billion and 1600 million. The boring billion is more informal, from about 800 to about 1800. So we can use them almost synonymously with that appreciation. So in order to evaluate this possibility, we need to assess plate tectonic indicators and the single lid indicators during this time. So the boring billion term, this is a rather depressing term that refers to nearly a quarter of the planet's history, spanning from 1.8 to 0.8. It's thought to have been nowhere near as dynamic and changeable as the planet today, but instead rather slimy and static. That's from a Cosmos website. Another one is the mid-Prerozoic has long been recognized as a unique time in Earth history for the roughly billion-year lack of evidence for either continental glaciation or significant variations in the carbon isotopic composition of marine carbonate, earning it the name boring billion. And then the period 1800 to 800 million years, marking the middle age of the Earth, overlapping with the dawn of the Neoproterozoic, is dubbed the Boring Billion or Barren Billion and is considered as the dullest time in Earth history. So Boring Billion, I put that in a while back, and the 235,000 results. So it's a pretty common word term. So number one, plate tectonic indicators, as we described them before, are missing from this time period. That includes the ophiolite. Well, there are some ophiolites, but there aren't that many. The subduction indicators, there's no blue schist, there's no lawsonite bearing metamorphic rocks, there's no jadeite, and there's no ultra high pressure metamorphic rocks. So the plate tectonic indicators are missing. Does that mean it was single lid? No. But on the other hand, it's certainly consistent with that interpretation. We're going to have to go to positive evidence for single lid. And what might that be? So the absence of PTIs, some people would say it's just a preservation problem, absent, you will hear people say absence of evidence is not evidence of absence. Okay, that's true. But absence of evidence is also possibly evidence of absence. It doesn't require it, but it's possible. I mean, we all recognize the record of Earth history is increasingly destroyed with time. Maybe all of the Mesoproterozoic plate tectonic indicators have been removed by erosion. So in order to make further progress on this point, we need to define single lid indicators and also examine if pre-Mesoproterozoic plate tectonic indicators are preserved, right? So if the argument is there's no plate tectonic indicators in the Mesoproterozoic, and there's no plate tectonic indicators from older times, then the erosional argument, tectonic argument, is more powerful. On the other hand, if there is evidence of plate tectonic indicators from before the Mesoproterozoic, then it's not obvious that erosion or tectonics removed them from the Mesoproterozoic. So what might be good single lid indicators? One of them is drier magmas. So for example, if you don't have subduction, deep subduction, we know delivers a lot of water to the mantle. If you didn't have that, then you might expect drier magmas. And we have examples of those in the form of anorthosites and A-type granites. There would another plate tech single lid indicator might be evidence of an elevated thermal regime, because plate tectonics is a very good way to insulate the convecting mantle. Plate tectonics is a very good way to cool the convecting mantle. The absence of plate tectonics can lead to a kind of an insulation, allowing the interior even to warm up. And another is passive continental margins. So passive continental margins form as a result of the Wilson cycle, and they're expected. If you have the opening of new oceans, you expect to have new passive margins. So if you don't see them, that's a kind of evidence for not plate tectonics, single lid tectonics. So here are the single lid indicators as Stern 2020 produced them. Dry magma indicator 1, dry magma indicator 2, the insulation indicator, and the no continental rift and drift indicator, passive margins. So these are compilations from others. Single A-type granites are, a kind of alkali-rich, anorogenic, and relatively anhydrous granitic magma, very distinct. There are some in younger rocks, but the Mesoproterozoic, this time interval, they dominate, very common in the Mesoproterozoic. Anorthosites are very unusual rocks. These are plagioclase-rich rocks, and this is mapping the area of them, not the number of them. And you can see the area of them is hugely greater in the Mesoproterozoic than there are in younger times or even older times. the thermobarometric ratio, which we've already talked about with the work of Brown and others, it's kind of hard to see here, but it's actually at a maximum during the Mesoproterozoic and then decreases more recently, as you might expect from plate tectonic cooling. And the continental rift and drift indicator, passive margins, this is Bradley's compilation. So ones where he was more confident, they're in black, and less confident, they're in white. And you can see, sure, we have lots of them today, but even back into the Paleozoic and the Neoproterozoic, there's significant numbers, but not significant numbers in the Mesoproterozoic. And then here we see them again in this Paleoproterozoic time. Now, there's also ore deposits. The economic sector of geology has its own interests, and they've been studying things like certain kinds of ore deposits, karunas, iron oxide, copper, gold, and ilmenite and orthosite. These are very common in the Mesoproterozoic. And in contrast, things like that require fluid-rich mineralization styles like orogenic gold and porphyry copper deposits, they are very common in Neoproterozoic and younger, and interestingly also in the Archean, but they are completely missing from Mesoproterozoic. So ore deposits can be taken as a kind of plate tectonic and singlet tectonic indicators. So now let's look at evidence for the earlier episode of plate tectonics that we referred to here. We've looked at this episode, we've looked at this episode, and now let's look at this episode. So this is this Orosirian plate tectonic episode. And one of the things we can see here is the zircon uranium lead age peak shows that the Orosirian was an important episode of continental crust formation, right? These peaks somehow reflect the amount of continental crust that's being produced. And if we look at the distribution of Orosirian ophiolites and eclogites, which we think are related to subduction, we see that they're pretty much on all of the continents. So the ophiolites are shown with these blue circles, and the eclogites are shown in these red dots. This suggests a global plate mosaic at this time. So some people have used the term the great Proterozoic accretion or orogeny to describe a long-lived global episode of arc accretion, continental growth, and orogenic amalgamation that built the supercontinent Nuna Columbia. And they refer to the 2.2 to 1.8 billion year period. So this is pretty widely accepted that there was something like plate tectonics going on in this time period. Now, Orosirian metamorphic style includes some low temperature, high pressure rocks. So this is the compilation of Brown and Johnson. So here we're plotting the temperature of pressure, degrees centigrade per gigapascal versus age. And here we see these, I draw your attention to these blue dots. These are the plate tectonic subduction related things. And you can see they disappear sort of here with one exception until the Orosirian. And these metamorphic rocks, they're not blue schists, but they have similarities to blue schists. So they're also consistent with this is a time of plate tectonics. So, and now passive continental margins, as we said, are generated by continental rifting associated with the Wilson cycle and plate tectonics, right? So here we've got the Wilson cycle, continental rifting, formation and passive margin formation, then subduction initiation, subduction and collision. And if we look at this distribution of passive continental margin formation, this is Bradley's compilation. This is Condi's, slightly more recent. Now, Bradley is plotting the number of passive margins as he saw it by start date, and Condi is calculating the average length per bin times 10,000 kilometers. Both of them see a peak, sort of an early peak here in the Paleoproterozoic. There's relatively fewer down here in the Mesoproterozoic. So the bottom line that I'd like you to walk away with is that plate tectonics started twice in the last 2.5 billion years. You know, the more recent one in the Neoproterozoic, but an earlier one that lasted for about 300 million years in the Paleoproterozoic. And in between that was a single lid episode. Now, having two episodes of plate tectonics helps us solve the thermal catastrophe paradox. So basically, this says that given Earth's present cooling rate, it should have been completely melted about 1.5 billion years ago, and we know it wasn't. So this comes from the Urey ratio. So the Urey ratio, U sub R, is very simple: the solid Earth heat production divided by the heat loss. So here is the cooling rate predicted by a Urey ratio of about 0.3. So right now, Earth loses about 45 terawatts of heat per year. The question is, what is the internal heat production? And two ways of estimating that, one from chondritic Earth models and the other is from measuring the neutrino flux, indicates about 20 terawatts of internal heat production. So the Urey ratio is less than 0.5. And what we see is the thermal evolution of the Earth as we've reconstructed from these basalts back to about 2.5 billion years ago, is that it was much slower. So if we had two episodes of plate tectonics separated by a single lid episode, then we could have relatively high Urey ratio associated with plate tectonics, Urey ratio of 0.3, and then a much higher Urey ratio associated with single lid episodes when the heat loss was reduced and so the cooling rate could somehow follow that. So basically the idea that the Urey ratio changed over time as a result of changing tectonic regimes. So I thank you for listening. If you want to learn more, please visit our YouTube channel. We've got short videos on some of these topics on our YouTube channel, UTD Geoscience Studios. These are the ones that you might be interested in: Evolution of Life and Plate Tectonics, which was an AGU talk. Another is Biogeodynamics, how Earth's tectonic evolution is reflected in its biosphere. The plate tectonic pump. Emergence, a chaotic system pushed into organization. Formation of new subduction zones by lithospheric collapse next to a fracture zone, and then subduction initiation in nature and models. So thank you very much. And if we have time for questions, I'd be happy to answer them.